Hi, everyone. Welcome to the seminar. Today, we are excited to have Juan Perdomo speak in our seminar. Juan is currently a final year graduate student in the ECS department of UC Berkeley, where he's advised by Moritz Hart and Peter Bartlett. His research is around the foundations of machine learning within social systems. He got his bachelor's in CS and math from Harvard, and he was previously supported by an NSF graduate student research fellowship. And today he's going to tell us about the many performances of performative prediction. Take it away.
Hi, it's very happy to be here. Thanks everyone for coming to the talk. So you mentioned I'll be talking about the many performances of form prediction and and please interrupt if there's questions halfway through. I don't think there's that many of us here. So the motivating observation, let's see. So the motivating observation for today's talk is that social predictions are causal. So what I mean by social predictions, these are predictions about people and meant to inform decision-making by part of humans. And an example of the kind of prediction that I want to have in mind here is this idea of predicting which students in high school will graduate on time. So the idea is that a school will use a machine learning system to predict which students are at high risk and low risk of graduating. And they're causal in the sense that these predictions can actually impact the predicted outcome. So the predictions are used very explicitly with the intent of informing school decisions by part of counselors or teachers, and hence can play a role in assigning interventions as to which students get help, and hence can impact the true probability of graduation, right? So we have this feature where the prediction that we're making is influencing the true probability of the outcome that we're observing. And sort of given this influence of prediction to the observed data that we see, the kind of main question that kind of comes to my mind is that, given that predictions influence outcomes, what even is an optimal prediction, right? Like, what are the goals of prediction in these settings? Okay, so kind of having that in mind, there's many answers, and maybe the classical answer to this question, coming from the supervised learning perspective, is that prediction is really about forecasting, right? So forecasting is this idea that there is some event, some future outcome, and we want to find a prediction function which takes in some prediction features x and outputs some output h of x, and we want this h of x to be close to y, where y is this future outcome. So in the education setting, that looks something like the following, right? There's this thing called graduation day, which happens at some point in the future, and a prediction is optimal if it matches, if it tells us exactly who will and who will not graduate on this future day, right? So who will walk on the stage and who will not. Good. So, but maybe a different sense in which we might think of a prediction being optimal is if it steers the distribution towards desirable outcomes. So I'll use this idea of steering as the goal of finding predictions that induce desirable outcomes. And here I'm really leveraging this kind of causal notion, or this causal sense of prediction, right? So I want to find a prediction h of x such that this prediction changes my the future outcome y, so that it is closer to some, target outcome variable y target, okay? So again, going back to the education example, we say that if our predictions have the ability to change which students will graduate, or the likelihood that students will graduate, then a prediction is maybe optimal in the sense of steering if it maximizes the true probability of graduation, okay? So kind of the thing I want to highlight here is that once we sort of acknowledge this fact that predictions have the ability to influence things, the goals of prediction are sort of inherently ambiguous, right? There's a much larger design space as to what we should be shooting for in terms of our predictions. And it's often not obvious a priori, like what the right objective should be, right? Reasonable people might have very different opinions, and both of them could be right as to what the goals of prediction should be. And so kind of the motivating question for today's talk is, how do we embrace this ambiguity in design prediction systems that kind of embrace this, right? Any questions so far? Good. Cool. So the outline for today's talk is I'll start by giving an overview of performative prediction and in particular outcome performativity. And this is a formal framework for reasoning about these kinds of problems where the predictions can actually impact the data distribution that we'll observe. So this will be sort of like shared background for those of you who may not have seen it. And then once I've introduced the framework, I'll talk about a new solution concept that tries to explicitly deal with this distinction between steering and forecasting, which I call performative omni-prediction. And then at the end, I'll talk about algorithms. So showing actually how can we actually learn decision rules that satisfy this solution definition. Good. So kind of starting with the, so I should say that this is joint work with Moritz Hart, Michael Kim, Celestine Mandler-Dünner, and Tiana. Moritz and Celestine are both at Max Planck in Germany. Mike is at Berkeley, and so is Tiana. So starting with the framework, maybe the best way to understand performative prediction is by analogy to supervised learning. So in supervised learning, I call this like the traditional approach to prediction, we say that our population is modeled by some fixed distribution over pairs X, Y. So we say students in our schools have some features X, and then there's some binary outcome Y, whether they graduate or not. And this population is kind of static and it's unaffected by our choice of predictor, right? So the value of a prediction rule is measured by the expected risk. So we have some loss function, and we measure the expected value of this loss function over this fixed distribution T, right? And the goal is here, this loss function usually captures a question of forecasting. Like think about the 0-1 loss, okay? The main issue with this formalism is that we can't talk about the causal impact of prediction, right? So this distribution is fixed, it's static, it's unchanging. It doesn't matter what we predict or how we predict this, the outcomes and feature distributions are always the same. Okay, so this is kind of like the main difference to performative prediction, and what I call the performativity thesis is that social predictions actually actively shape data distributions, right? So here the population at a technical level, the main difference is that the population is no longer some fixed data distribution, but rather it's modeled by some distribution map, D of H. So this is a function from decision rules H to distributions over pairs X, Y. So the idea is that if we make predictions according to a particular classifier H, then we'll observe data that's sampled from D of H. Okay? Does that make sense? Any questions? So given that predictions can impact the data distribution, we measure the performance of a predictor in the performative prediction framework by the performative risk. And here is exactly what you might imagine it to be. It's the expected risk of H over the distribution that H induces, right? So I've highlighted here in orange the kind of like the main difference with respect to the risk in supervised learning. So the performative risk of a classifier H is just again, some expectation of some loss function. But now we take this expectation over the distribution that H induces. Okay. And this loss function may no longer always be just something like the 0-1 loss. We should think about it more generally, and it's something I'll come back to. So once we kind of recognize it, I think we start to see performativity everywhere. So this idea that predictions impact the data distribution happens in recommender systems, it happens in traffic forecasting, it happens when we predict the probability of disease. So here I've been talking about this education example, but hopefully you'll believe me when I say that performativity exists much beyond this education setting. And sort of for today, I'll be focused on a special case of performative prediction in which the predictions only impact the distribution over outcomes Y. So in full generality, in performativity, H, when we deploy H, we see data from D of H where the features and the outcomes can change. But in outcome performativity, we think about the following data generating process where we sample some feature X from mixed distribution D. So this is like GPAs and demographics of 5th grade students in our school, and that doesn't change by our prediction. We make a prediction, maybe say at the beginning of high school, based off these features, and then we observe some outcome. Sorry, I'm getting over a cold. So we observe some outcome Y star, and maybe for today, let's think about this outcome as being just like a Bernoulli. This is just for conceptual simplicity. And the key point is that the parameter of this Bernoulli is a function of the features X, but it's also a function of the prediction Y prime. So this is highlighted here in orange. Okay. So the binary outcome is not crucial, it's just for simplicity. And this kind of matches like the normal flow of time, right? We observe features, given these features, we make a prediction, and then the outcome is something we observe in the future, and it's affected by both my features and my prediction. Good. So for those of you who might be familiar, right, performative prediction is a general framework. It encapsulates strategic classification, where you, in strategic classification, like X's change, and in outcome performativity, X's are fixed, and the Y's change. So that's kind of like the background that I wanted to go over in terms of performativity. Now I'll move on to sort of how do we address this question that I posed earlier regarding how designing prediction systems when there's many goals that we have to contend with. So kind of to frame this, there's this question of like, what is a loss function, right? So in my view, a loss function is just a way of expressing preferences over data prediction pairs, right? It says we like certain data prediction pairs over others. So for a forecasting problem, forecasting, if the goal is to find predictors which maximize some forecasting objective, we pick loss functions that mathematically express this idea that I want my predictions to match future outcomes. So the classical example of such a loss function is the 0-1 loss, right? So it's 1 if my prediction H of X does not match Y, otherwise it's 0. But we can think about other loss functions, right, that have expressed a different preference relationship over data prediction pairs. For example, steering. You know, I want my predictions to induce particular outcomes. Here, this loss function doesn't depend on H of X at all. Right? It's just a function of Y. And the influence of H of X is kind of implicit, right? Because we're saying that H of X affects the distribution, and we just want to find the distribution that maximizes the probability that Y takes on a particular value. And yeah, so it ignores H of X. And going back to the framework, we say that a decision rule H star is performatively optimal if it minimizes this performative risk over some class of decision rules, capital H. Right? So in other words, it's performatively optimal if H star maximizes my preferences as expressed by my loss function over some class of rules in H. Okay. And previous work in performative prediction had thought about, you know, how, given a loss function, how do we find the performatively optimal solution for this loss function? Oh, and I guess I should say I'll use this notation. So the performative risk of H and loss is just when I should make decisions according to H and I measure according to the loss function loss. Any questions so far?
I have a question.
Yeah.
How's the mapping from classifiers to distributions defined here? Does that matter, or could it be a general mapping?
Yeah, so it's just the mapping is just the outcome performativity mapping. So it's features are static, make predictions somehow, and then I observe some outcome Y star, and I'm making no assumptions on this P star function. So this is just a function from x's and y primes to the unit interval.
Okay, got it. Thanks.
This is for the context of this talk. There's other conditions on D of H in different setups.
I have a question.
Yep.
So do you think about features as being historical or immutable features? Like ones
Yes.
that cannot be changed as a function of the decision? So what's the intuition?
In outcome performativity, we make the explicit assumption that the features are static. So they're not influenced by the choice of predictor. Yeah. So think about in the education example, my features are things like demographic information,
Right.
historical test scores, things that exist before I even like deployed my predictor. Okay.
Got it.
Good. So going back to this idea of performative optimality, right? It's just the decision rule that maximizes my preferences. But as I pointed out previously, the issue, or like there's a few issues with this definition, and it's that committing to a single right objective can be hard, right? We mentioned that there's a much larger design space once we recognize that predictions are causal, and it's kind of hard to understand exactly what the right objective is, especially if we haven't understood the influence of our predictor. Like we don't, maybe before we deploy something, we don't have an exact understanding of like how our predictions influence the data distribution. And we want to allow ourselves some flexibility, right? So like if we make a mistake, we learn something new, we'd like to change the objective, right? And then different objectives can have drastically different decision rules, right? So for example, you know, a loss function that if we like to steer to 1 versus 0, is in the case that outcomes are binary, the optimal decision rule can be like drastically different. And this is kind of different than in the forecasting sense, right? Like cross entropy, squared loss, 0-1 loss, you know, all of these different loss functions, they're, you know, mathematically different, but they all kind of like shoot for the same thing. Whereas once we think about steering losses, you can shoot towards very, very different things. Okay. So how do we try to adjust this in this work? And the solution is to try to like avoid choosing one loss function, right? The idea is that we want to learn a single model that given a particular loss function, we can easily modify or like tweak so that it's optimal for a large number of different objectives. Right, so you should think about this as like a menu of optimal decision rules, and choosing from this menu is like very easy. It's like tweaking a parameter in your code, and it should take like, you know, constant time to change it. It's something that is very flexible, and we don't need to like retrain, collect more data. It's inexpensive. Good. So this is kind of like the high level intuition. And the formal definition is this idea of performative omni-prediction. So this is a concept that was introduced recently in the supervised learning setting. And here we're extending it to the performative prediction setting, where I think it becomes maybe even more interesting because of this idea that like the loss functions can be, you know, there's no relationship across the different objectives, right? They can mean qualitatively different things. So formally, a performative omni-predictor is a function that from features x and predictions y prime to the unit interval. And it's defined in terms of 3 parameters. One is this class L of loss functions. So this set capital L is just a set of different loss functions. And we have a set capital H of decision rules. So these decision rules, you think about them as like hyperplanes or like decision trees, whatever it is that we're actually we want to compare to in terms of making predictions, and some approximation parameter epsilon. And we say that this predictor P is a performative omni-predictor if for every loss function in L, there exists some simple function pi that takes into account the particular loss and the omni-predictor P, such that if we make predictions, that we make decisions according to this simple function, then the performative risk is about as good as the best decision rule in H. So this is a lot. We'll sort of slowly parse through this definition. Okay, but At a high level, I want you to keep in mind that there's some set of loss functions. This is like the set of things we want to be optimal with respect to. A decision rules, which is like our baseline. What are we comparing to? And we're saying that for every loss function in L, I can tweak my predictor P. So this pi L of P is the tweaking, such that this tweaking induces a decision rule that is approximately performatively optimal. So we'll give a little bit more intuition exactly what this simple function is. Yeah, so this extends work by a number of others to performative prediction. Good. So maybe before getting into exactly what this pi L is, I'll maybe give a bit more intuition as to what this definition is saying and what it's not saying. So omnipredictor is a one predictor that's like simultaneously optimal for every loss. And these losses can be arbitrary, like they can be steering losses, they can be forecasting losses. They can encode, particularly they can encode contradictory goals. We're not making any assumption as to how these things relate, right? So it says, and it's optimal in this like per loss function sense, right? For every L in L, I'm optimal with respect to the best decision rule in H for that loss function L, okay? Intuitively, what this is doing, it's like front loading all the learning, right? It's like a way of achieving flexibility. So I find this predictor P, and I have this very strong guarantee that if I tweak P, I'm going to be making optimal decision rules with respect to any L, or I'm doing as best as the best H and H for that L. Okay, so this is what omniprediction is. It is not it's not doing robust optimization. Okay, so it's not solving some min-max objective, right? We're not doing something that we pick the best H and H such that if we maximize over the loss functions in L, we do as best as we can. Because I'd like to convince you that this robust optimization objective is actually like a pretty weak definition if our goal is to really achieve flexibility, right? So, for example, have in mind a steering loss that steers to 1 versus a steering loss that steers to 0. If we want to solve this min-max objective, then we just kind of like split the difference, and we end up with some predictor that's not really informative for either one, right? And the key difference with respect to robust optimization is that in omniprediction, we allow ourselves this ability to kind of tweak the predictor, right? So you tell me the loss function, and then I tweak my predictor according to that loss function. So I mentioned this like pi L sub P, which may be mysterious if you haven't seen it before. So I'll give a little bit more intuition as to what this is, and maybe the best way to understand it is by kind of understanding what this means in the context of like supervised learning. Okay, so we think about this pi sub LP as like a post-processing. Okay, so maybe going back to kind of learning theory 101, let's assume that you have some outcome. This is in supervised learning, not performative prediction. So if you have some outcome variable y that's distributed according to it's some Bernoulli random variable, and I tell you that the Bernoulli has some parameter p, a p of x. So what is the post-processing if I want to be optimal? All right, so what is the given p and the knowledge of the loss function L, how should I post-process L and P to find the best decision rule for this particular loss? So in particular, what is pi of L sub P for something like, say, the squared loss? Someone should jump in. Okay, maybe I'll do the first one, and then someone will do the second one. So like, you know, it's just a conditional mean, right? So the squared loss is like the prediction rule that minimizes the squared loss is just a conditional mean, right? So pi of L sub P knows P, right? This is like an input to the post-processing. So if we want to minimize squared loss, we just output it's just the identity. It's like P of X, right? Now what about 0, 1? Oh, 0, 1 loss.
Threshold at 1/2.
Yeah, exactly. So we just say 1 if it's like above 1/2, or 0 if it's below, right? So we just have the most likely outcome. And kind of like the intuition I want to convey is that if you knew P, then this post-processing is like a very easy thing to do, right? So if I knew this like true probability P star, like nature's P, this post-processing is very easy, right? In particular, if P star is the truth, right? So like if Y is Bernoulli and with parameter P star, then P star is in fact an omni-predictor for any set of loss functions, decision rules, and tolerance parameter, right? Because like given P star, we can always just minimize the conditional risk in a pointwise sense, right? So given X, we can compute this expectation of Y star, where Y star is distributed according to P star. It's like a Bernoulli. I'm using this like sim P star to denote that Y star is Bernoulli with parameter P star. And I just find the prediction Y prime that minimizes this conditional expectation. So this is exactly what I was doing in the previous setting, in the previous slide, right? This argument for the squared loss is just a conditional mean, and the argument for the 0, 1 loss, if Y prime is discrete, is just the most likely outcome. And I want to try to convince you that the same idea holds in performative prediction. But maybe I'll stop here. Are there questions about this post-processing? Did that make sense? Make sense? Good? Okay. We'll maybe move on. I can't see the chat, so if there's any questions in the chat, maybe Said or someone can mention those. Good. Okay, so in performative prediction, we can take the same idea and push it forward. So the post-processing in the performative case is that so P, this omni-predictor, is not just a function of X, it's also a function of Y prime, right? Because like it's saying like what is the probability of the outcome given that my features are X and I make a prediction Y prime. And this post-processing looks very similar, right? So given a feature X, I can just find the prediction Y prime that minimizes the conditional performative risk given X, okay? And this minimization, the loss function depends on Y prime, but so does this like conditional expectation function, P star. But if Y prime, like the set of the space of predictions is discrete. So say like you have categorical predictions, 0, 1, high, low risks for students, then this argument can be computed just by enumeration, right? For every single Y prime, Y is just a binary variable. So this expectation is just the sum of 2 terms that I can compute in closed form because I know what P is and I know my loss function. And to find the minimizer, I just can cycle through all my predictions and find the one that minimizes this value, okay? Does that make sense? Good. So kind of the first theorem is that, we didn't make any assumptions on to what the truth that P star is, right? Sorry, so maybe going back, right? In the same way that in supervised learning, if I knew the truth P star, like the true probability of the Bernoulli, then this is an omni-predictor. The same result holds in performative prediction, right? So I said that Y star is a Bernoulli with parameter P star, X and Y prime. So if I knew P star, this would be an omni-predictor, okay? But this P star could be arbitrarily complicated. It's just some function from X and Y prime to the unit interval, right? This function can be hard to compute. Like it could, require a very large circuit. It could also be very hard to learn statistically, right? It could be arbitrarily non-smooth. So the first theorem says that regardless of what nature is, there always exists some function P star that is an LH epsilon performative omni-predictor, and the complexity of P is independent of nature. Like how complicated this function P is only depends on how complex my functions in L are and how complex H is. So in particular, if L and H are simple functions like, hyperplanes or 0-1 losses, things that I can very easily compute, then P is also easy to compute. Okay. And yeah, so it doesn't depend on the complexity of nature, which could be some very difficult function. Right? And this theorem is constructive. Right? We can actually, this is an existence result, but later on we'll talk about how exactly we find this P star whose complexity only depends on these parameters. Good. Okay. So we talked about omni-prediction, like the definition, what it means. We mentioned that omni-predictors exist. Now we'll talk about algorithms for performative omni-prediction and actually how we go about learning, how we go about achieving this definition. And at the end, I'll have some conclusions and kind of synthesis and summary of what we did. So the idea is the following. So we mentioned that P star, like the truth P star, nature's model of outcomes, is an omni-predictor, right? It's an omni-predictor for any class of loss functions and any decision rules H, right? And the goal to how to build an omni-predictor that's learnable is that if we can find a model P that looks like nature's P star from the perspective of a set of efficient tests, so it satisfies some notion of computational indistinguishability, then P really is as good as P star for the sake of omni-prediction. Okay, so we just need to be able to sort of fool some set of distinguishers, and if you can't tell whether it's P or P star, these distinguishers can't tell whether it's P or P star, then P is really as good as P star for omni-prediction, right? So this is kind of like the high-level intuition behind how these technical results work. So I'll now try to like formalize what is this idea that it like looks like nature and what are these tests, right? So the definition of indistinguishability that we work with is this idea of performatively outcome indistinguishable. So performatively outcome indistinguishable is a property of a predictor P. So this P satisfies the same type as an omni-predictor. And it's defined in terms of a set of losses, capital L, and decision rules H, and again, some approximation parameter epsilon. And we say that a predictor P is LH epsilon performatively outcome indistinguishable if for any pair of decision rules H and loss function L, the performative risks are similar. So let me walk through the differences between these two terms. So here on the left, this is just the performative risk of a decision rule H as measured by some loss function L, where outcomes are sampled according to P, right? So given any X and H of X, this P is something that we can compute, right? It's something that we've learned. And we just flip a coin with probability P, and that's what the Y is. And on the right-hand side, we do the same thing, but this Y star is sampled from nature, right? This is like, what did a student graduate or not when I had features X and made a prediction H of X. And we're saying that for all choices of H and L, these performative risks are close in absolute distance, in absolute value, up to some error epsilon. Okay. And the main theorem is, and the kind of like the intuition is that each pair of loss function and decision rule defines some performative risk, and these are kind of like the test functions that we want to measure closeness between our model and P star. Okay. And if we're like close from the perspective of these test functions, then this is like the theorem is that this is an omni-predictor. Okay. So more formally, given a set of losses and decision rules, which is always kind of like the these definitions are defined in terms of if a predictor satisfies this indistinguishability criterion for every loss L in L and H prime, then P is an LH O epsilon performative omni predictor. And here there is a subtlety where, you know, I'm requiring that P is indistinguishable from nature, not just for H, but for a slightly augmented class of decision rules. This is H prime. Sorry. So these decision rules, what this augmented class, what it means is that I'm including the post-processings of P as decision rules. So it says, like, you know, P is indistinguishable from P star from the perspective of H. It's also indistinguishable from P star, even if we act according to P. Right, so these pi L sub P, this set has size of capital L many decision rules. And this kind of intuitively means, like, what is, like, if we were to treat P as the truth and L as our objective, then we would act according to pi of L sub P. And I'm requiring that P remain indistinguishable from P star, even if we act according to P. Then the theorem is that if P satisfies the instability condition, then it in fact is an omni predictor, okay, for the class H instead of the general L. Yeah. So far so good.
Can I ask a question?
Yeah.
So functions in H take a feature vector X and output a prediction, right?
Yep.
But pi LPs take a number between 0 and 1 and output like another number.
No. So pi L sub P is the same type as H. So going back, pi of L sub P takes in a feature vector X, and it still outputs some prediction Y prime. It uses P, like the number in 0, 1, as a helper function to solve this argument, but the type of pi sub L sub P is the same as H, right? It just it outputs some Y prime. Okay.
I see.
But is Y prime in a finite set or in a infinite set?
Y prime is some finite set here. Yeah.
Because you gave the square loss example.
What?
Because you gave earlier the square loss example.
Oh yeah. For the squared loss example, you think about some continuous, but you can think about binning the unit interval. But yes, for the sake of this talk, Y prime is some discrete set, and that's kind of important for the sake of computing this argument, right? It's not clear how you would do this argument if Y prime were not discrete. Although, you know, I don't think that there's very many it's not too hard to solve 1D optimization problems. Good. But yeah, it's an interesting question. How do you extend all these ideas? Because at a technical level, the results really do hinge on the set of predictions being discrete. And I don't really know how to solve the case where they're not. And I think that's an interesting question. Great. So we were here. Good. So this sort of the main idea that I wanted to kind of convey in the slide is just that, you know, indistinguishability implies omni prediction. And this theorem is quite nice because it gives us like a very concrete goal as to how we should achieve omni prediction, right? Like it says indistinguishability implies omni prediction, so we're fine with just achieving indistinguishability in this very concrete sense. And here we can kind of like use this boosting style algorithm that's become very common in previous work on omni prediction, like multi-calibration and that set of this part of the literature. And the idea is that we we build up some to achieve omni prediction. We run this iterative algorithm whereby we initialize with some arbitrarily bad function that it maps x's and y primes to the unit interval. So just like for simplicity, let's assume that we initialize at a half. And then at every round, we solve the following task. We try to do this auditing step. So I mentioned that indistinguishability is defined in terms of the set of test functions, right? And if we satisfy distinguishability for every test function, then we're done. Right? So the idea is that at every round of this algorithm, we'll try to find a test function defined in terms of some pair H and defined in terms of some pair of decision rule H and loss function L, for which our current model P sub T is not indistinguishable from nature, right? If for some reason no such function exists, then it's very clear that we've found something that's indistinguishable, right? Because that's just directly the definition of indistinguishability. It means that we are indistinguishable from P star for every H of M. So if we can't find anything, we terminate. However, if we do find a pair for which PT is significantly different from P star, right, where significantly is sort of operationalized through this parameter epsilon, then we essentially do what looks like boosting, right? We like add a circuit computing H and L and add it to PT, and we can prove that this boosting step kind of brings us closer to P star. And kind of the theorem, right, is that this algorithm will actually terminate, right? From writing it down this way, it's not obvious that we would ever get to this like termination condition. So this is something we can prove. And yeah, for those of you who might have seen familiar with like boosting style analyses, it looks very similar to that. So I should mention that, you know, I've written this algorithm in a very kind of like abstract way, right? This like find H and L such that PT is different from P star, right? This we don't assume that you know P star, right? But you can have samples from P star, right? We have some data set and we can observe like what is the outcome given that features were X and I made a prediction H of X. So there's statistical question of like, you know, how much data do I need to implement this auditing step? And there's also a computational question, right? Like how much computational resources do I need to implement this search algorithm, which looks over all H's in H and loss functions in the set capital L, okay? So we need assumptions to make this work. So I'll give a little bit of an overview of what are the guarantees that we expect, or guarantees that we prove from this indistinguishability algorithm. But at a high level, the idea is that this auditing step effectively reduces to supervised learning, right? So even though we're in performative prediction, where different predictions can induce very different distributions, we show that there's kind of this surprising reduction to supervised learning, right? So all the primitives you need really are just supervised learning primitives. You don't need sort of stronger statistical or computational oracles than what you need to solve basic supervised learning problems, in particular cost-sensitive classification. So the theorem is the following. So we need, as I mentioned, statistical assumptions and computational assumptions. So the first one is a statistical condition. So if we have access to an exploratory data set, where for every X, the prediction assigned to this X is drawn uniformly at random from the set of all predictions. So think about the case where Y prime is just the set 0 or 1. My data set consists of n IID examples where for every X, I flipped a coin Y prime, that's, you know, 1 or 0 with equal probability. And then I observed the outcome Y star, that's a Bernoulli with parameter P of sample with parameter X and Y prime. And this is kind of like gives us a notion of coverage, right? Like we observe how people respond under different predictions, and this is kind of necessary. Some notion of coverage is necessary. And on the computational side, we assume that the decision rules H are learnable. So for every fixed loss function L, you can solve cost-sensitive classification over H. Then the indistinguishability algorithm is both statistically and computationally efficient, and it returns a performative omni predictor. kind of more formally, the algorithm will terminate in O of 1 over epsilon squared many iterations, and it'll return an omni-predictor. And each iteration effectively reduces to solving cost-sensitive classification problems for every loss function in L. I'll stop for questions for a
Juan,
second.
can I ask a question here?
Yeah.
So okay, cool. So you've like written down this outcome indistinguishability problem that has sort of a bandit aspect to it. There's things that you only observe when you try the particular action.
Yeah.
And then the algorithm you've given is sort of like an explore then exploit kind of algorithm. Like you have data that is sort of pure exploration data. We're not trying to predict well, we're just predicting random wise. And then you're training your model and then you're going out and deploying it.
Right.
I guess like in general, exploit algorithms tend not to have optimal regret bounds. So have you thought of sort of a bandit version of this where there's no separate training and deployment phase? It seems like there might be sort of an algorithm that has better regret bounds if you don't separate exploration from learning the way you are here.
Yeah, you're absolutely right. So we did the sort of like the absolute like naive thing that you might try, which is exactly what you're describing. Just like, have this completely uninformed search where you just predict completely randomly and then optimize based off that. But I think there's a lot of there's an interesting question as to how do you do sort of guided exploration, adaptive exploration, such that you get faster regret bounds? Because you're right. The naive thing is not going to get you the right regret bound, and it's not something that I don't know how to do it, and there was just like a lot of stuff going on, so we didn't focus on over optimizing this part too much. But I think it's an interesting question. I mean, there's also this interesting question of, we have like this idea that you can make predictions completely at random is not true, right? You can't run experiments on children, right? You can't predict randomly on, if we're thinking about this education example, you can't assign predictions random. So like, how do you do this off of offline data, or really minimizing the number of like exploratory samples you need? I think it's a pretty important interaction to make these things practical.
Right. Yes. Like sometimes you can get exploration for free with greedy optimization if you assume the covariates are sufficiently high variance.
Exactly. Yeah. So I didn't include the rates here for like computation and statistics, but like, this is all sort of like a small polynomial in all the problem parameters. Like, statistically, you would depend on log the number of decision rules, log h, which is just like VC dimension of h. And in terms of epsilon, it always scales like 1 over epsilon squared or 1 over epsilon to the 4th. And again, this is not something that we don't have a exactly sharp understanding of these rates yet. But yeah, so there's not a lot of time left, so I'll just try to kind of sum up and have some time for questions. So we started with this idea that, social predictions are causal. They have the ability to influence the thing that we are predicting. And this causality means that accuracy may not be the only goal. So there's this kind of like fundamental distinction between forecasting and steering. And I mean, this is a distinction in the sense that like conceptually, these two things are different. It could be the case that the optimal decision rule for forecasting is the optimal decision rule for steering. Like maybe if I predict that like everyone's going to graduate, this like boosts everyone's confidence. Everyone works really hard. They believe they can do it, and they also graduate. So it could be the case that these shoot in the same direction, but at least that doesn't necessarily need to be true for all problems. And we should think about the decision space of optimal decision rules as larger than in supervised learning. And what did we do? We defined this idea of omni-prediction and performative prediction. And omni-prediction provides flexibility to choose goals from a menu, right? But it doesn't necessarily tell us which objective to pick, right? It says that like, if you change your mind, you can quickly do the post-processing. You don't need to retrain. It's computationally efficient, but it doesn't exactly guide this process of like what we should pick. So I think this question is also kind of interesting. How do you figure that out? In terms of kind of interesting directions or open questions, there's this question we chatted about previously around, how do we do guided or adaptive data collection, both in achieving the OI definition and in choosing the loss function. And so this is kind of tied to this notion of regret. How do we get better regret bounds? And there's also, I think, interesting computational questions. So like, how do we find, so at a computational level, the algorithm, what it does, it runs a for loop over every loss function in the set L. So this doesn't work for like infinite, or at least naively, it doesn't work for infinite sets of losses or like all convex losses, things like that. So I think that maybe by exploring connections like multi-accuracy or multi-calibration in certain settings, like we know that it might be possible, but it's not clear. And one thing I didn't talk about at all during this talk, but it's in the paper, is that these omni predictors, you can make them robust to distribution shift in X. So all these optimality conditions, there's some fixed distribution D over features X, but we can ask for things that are optimal even if the distribution changes. And computationally, we deal with that as just treating it like a different loss function. So in some ways, like if we just think about steering losses, like there might only be 10 steering losses we care about. So paying linear in L is maybe fine. If we think about distribution shifts, there might be very, very many. So paying linear in L, it might not be great. So I think this is kind of like making the search efficient, I think is an interesting question. So anyway, thanks everyone for listening. I guess we have a few minutes for questions.
Yeah, thanks for the great talk, Juan. If there is any question, just unmute yourself and ask.
Sure, I've got another question. This is all very cool. So you phrased all the results for outcome performativity, but like, is there a way to phrase the results more generally in terms of sort of causal inference? So like somehow you're estimating treatment effects. So, if you wanted to like give the elevator pitch for this paper to someone who studies causal inference, is there like a different language in which you can state the main result for them?
Yeah, I think that, right, so you could think about the outcome Y star as just the potential outcome under, so you can think about Y prime, the prediction, as the treatment, and Y star, the realized outcome, is just the potential outcome.
Right.
So you're doing, I guess what's the right word in the conference? It's like you're doing some sort of counterfactual optimization. Right? I guess it's also very related to like contextual bandits, right? This is very similar to contextual bandits. We have some like set of features, you make some action, and then you see some reward. But there's not, it's kind of hard to reason about this idea of like multiple loss functions, multiple rewards in bandits. That's not something I've seen done, but I think that with regards to causal inference, yeah, I think it should be possible. I guess it's not always like, inference is a harder problem than optimization, in the sense that if you can do causal inference, you can always do policy optimization. But I think there's settings in which you can do policy optimization in which you cannot do causal inference. Like you can, like satisfying like OI definitions does not mean that you're statistically close to nature. Whereas causality is really about kind of like being statistically close to nature, right?
Well, right. I mean, I guess you're not exactly identifying the causal model, but you are doing causal inference in a way that gives you accuracy guarantees with respect to some hypothesis or
whatever. Yeah.
Anyway, okay, I need to think about that more.
Yeah. Good questions.
suppose I want the features to change too. Is there, do you know anything about how
Yeah.
sort of multi-calibration and omni prediction, what it tells us about that?
Yeah, so I think that's, I mean, it's a really interesting question that I don't know what to do about. I feel that this question of like what you anchor your predictor at is challenging in strategic classification. So in outcome performativity, there's a very natural notion of a unit. Like I see a feature X and I know that this is one person, and like if I make different predictions, I'll serve different outcomes for this person. But what is the unit in strategic classification is harder to think about, because there it seems like causality or influence can't be really grounded in my prediction, like Y prime. The strategic response is really a function of my function, right? Like if I want to compute the best response features, I need to know kind of like the classifier that you're deploying, because I need to sort of figure out for a, play this game of like, if I choose X prime, like, will I get this decision rule, that decision rule? So I'm responding more to your, like, my response is really a function of H rather than Y prime. And I think that this sort of, so that's kind of what I mean by anchoring. Like you have to, like the best response dynamic or the algorithmic influence is kind of modeled in terms of H, or at least the way I think about it. So coming up with the right notion in indistinguishability is more challenging. Like that's why I guess it's previous work had looked at like, how do I guarantee kind of like convexity with like my objective is convex in H, right? Because I'm directly optimizing over H, whereas in outcome performativity, I can like optimize over Y prime. And that's sort of like a simpler optimization problem. Like, I don't know how you do these, like minimize the conditional expectation in strategic classification, because it's not clear what you're conditioning on. But it's a cool, I mean, I don't know. I feel like it's not to say it's like impossible. I think it's an interesting question. I'm curious. And how do you do both simultaneously too? Cool.
Cool. Well, thank you.
Well, thank you everyone for coming. Appreciate it.
Thanks
Have a
for
great
it.
day.
Thank you.